I tell many people that I make videos for myself more than anything else because I have the worst memory in the world and I don't think they believe them. So today's video is an example of this. And these are magnetic equations I learned during my honours year or my fourth year at university. And since then, probably a year later, probably less straight after the exam, I forgot them and never felt I could really ask anyone what they meant because it would be a sign that I didn't know what they were. But thank heavens now for ChatGPT. We can ask a lot of things we should know or pretend we know, and ChatGPT can give us an answer. So I thought, well, before I forget them again in the next week or so, I'd make a video so I can go back and listen to myself. So first, before we get started, let's just look at this picture because that's a lot of what we're going to be speaking about today. So you've got a green body here that's been magnetized. It's in this external field, which are these red arrows here pointing to the left. And that tells you that we're at the equator because the field is parallel to the Earth, not at 90 degrees, which is what it would be at the poles. And so this body has been magnetized, and as a result, you have positives on the left here and negatives on the right, and that's setting up this induced field in the body, and that's these blue arrows. And so the blue arrows are coming out on the left hand, coming in on the right-hand side. And so the blue arrows and the red arrows combine together to give us this anomaly plot up at the top. And you can see on the left here, they're pointing in the same direction, so it results in this positive. In the middle here, they're in opposite directions, and so it gives us this low in the middle, and on the right-hand side here, they're both going towards the right as these blue arrows go into the body, giving us this positive. And so this is our induced field over the body at the equator, and we know that this profile will look different depending where we are on the Earth. So at the poles, it'll be a positive. In South Africa, it will be a negative in the south and a positive in the north. So magnetic responses really do depend on where you are on the Earth. Okay, so we have a bunch of equations that describe how the body responds to this external magnetic field, what type of anomaly it will form, or maybe the size of the anomaly, the amplitude. And so the first equation we're going to look at is this M is equal to KH. And sorry, I should have written that one a bit nicer. And so the main thing here that we're going to look at is that the K and the M link with the body's properties, and this H here is this external field. So how does this equation link in with this picture? So like I said, H is the magnetic field strength, the external magnetic field applied to the material. And this is according to ChatGPT. So H here really are these red arrows here. So it's not something we can influence, or the body doesn't link with the body, it's the Earth's magnetic field. The M and the K link with this green body itself. So the K is the magnetic susceptibility, you can see here, of the body. And I'm sure many of you have experience with magnetic susceptibility. You've probably measured in the lab or in the field. And it really is easily measured. It's in SI units, and it tells you how much magnetization is in, well, let's start here, a materials dependent proportionality constant. So it's really proportionality constant, but if you've ever seen the values in the textbook, it's not very constant. It's quite a range. It determines how much magnetization M is induced in response to H. And so what does that mean? It really just says when a material with a susceptibility K is in a magnetic field, H, what does its magnetic anomaly look like? And that's really talking about this M side here. So if K is very small, you might then get a small response here, even if the field is, which is in red, is very large. And so then we move over to M, so magnetization in amps per meter, and I should have said here magnetic field strength was also in amps per meter. So it says magnetic moment per unit volume of the material. It tells us how strongly material is magnetized when exposed to a magnetic field. And so I think the reason why I definitely blocked out this equation is there's just too much magnetic everywhere, and I never really understood what applied to everything. So I've read you all these definitions, but they're very wordy, especially if you're not a first language English speaker. But so it's all you need to really remember is that it's saying H is this red external magnetic field, K is the susceptibility of this body, and so how do those two result in M, or like, sorry, none of that sounded good, it's really just saying these red arrows plus this green body how big do they cause a response, which is the blue arrows here. So, and it's largely dependent on how big the external magnetic field is, but that's not something you can really influence. It's dependent on how big the susceptibility is of the body, and then both of those interacting together will give you these blue field lines. And so we're really just trying to determine how big is this field with these blue field lines, and how does that impact the profile that you measure here across the body. So I don't know if that did any better for you, but hopefully it'll help me next time I come back and watch my video. This was just to remind me and you about K. So K, if it's bigger than 0, it means the material is either paramagnetic or ferromagnetic. Really go ask ChatGPT more details about that. But your magnetite is an example of ferromagnetic, and then most other rocks are paramagnetic. So paramagnetic obviously is not as strong a response. But the main thing to remember here is the material get magnetized in the same direction as H. So if we go back here, you can see the magnetization here, this blue lines, on the same direction as these red lines. Whereas if it's diamagnetic, K is less than 0, the material develops a magnetization opposite to H. So, I mean, I don't know if it would be exactly the same here, but blue lines would be flipped in the opposite direction. So you can imagine it really will affect your anomaly that you measure over it. And then K is equal to 0, vacuum or non-magnetic material, there is no induction. Okay. And then how does this relate to magnetic permeability? Because we often speak about magnetic susceptibility, but what about permeability, which is mu here? And you can see mu is equal to mu naught, open brackets 1 plus K. And we know K from the previous equation. This is the magnetic susceptibility. Mu naught is a permeability of free space. So this is a value that doesn't change. It is a constant. And so what's going to change here is K. And so obviously then the permeability of the material is influenced by the susceptibility of the material. You can see here paramagnetic and ferromagnetic material, K is positive, we've just said, leading to a higher permeability, whereas diamagnetic material, K is negative, we knew that, which is reduces the permeability because of this bracket here. So we're now going to talk about magnetic permeability. Okay, so this is another equation that we are used to seeing. And you don't have to feel daunted by it because you now know what H is. H was that external red field. We now know what mu is. It's the permeability, and it links with the susceptibility. So, well, what is B then? And again, so this is why I always got confused with these equations, because you had M, H, and B. And I was like, I don't understand what the difference is between them. So hopefully now I understand. So we said here, H, magnetic field strength, amps per meters. It's this external magnetic field, independent of the material. It's that big red, those red lines. We know, like we said here, mu, a measure of how easy a material allows magnetic fields to pass through it. So you can imagine, because permeability, when you think about how permeable a material is, we're often talking about liquids flowing through a material, but now we're talking about magnetic field lines. How easily can magnetic field lines pass through a body? And I would assume, well, let's not assume anything. Let's carry on going. Okay, and what is B? So B on top here represents the total magnetic field. So this is both the external field, which is H, and the field induced in the material, which we spoke about before, which was the M. Okay, and so you can imagine here that if, well, I don't actually like how this is written, but anyway, let's keep going and then we'll play out some scenarios. Okay, we've spoken about this. So this equation states that H is proportional to the flux and inversely proportional to the permeability. And so B is the flux density. So let's just rearrange this equation a bit so we can understand better how these properties link with each other. Okay, so I've just rewritten the equation in a different way here down at the bottom, but let's walk through the other two. So this is the equation we looked at already. This is the susceptibility of the body. This is the external field. And M in blue here is this magnetization of the body. So how magnetized does it get? And then what we've just looked at here now is this H is this external field, so these red arrows. Mu is the permeability of the body, and this B is this magnetic flux. So flux here was dependent on both the external field and the field in the body. And so I think I don't like it in this form, or it doesn't make sense to me, because H is what we're changing. in this equation. So we're changing, sorry, H is what is being changed. We're changing B or mu to get a bigger or smaller H. But when it comes to geophysics, our H is pretty set. Like it's Earth's external magnetic field. We are not trying to influence it. So what we're trying to understand here is this B is magnetic flux. And so that's why I've rewritten it here. So remember H, these red arrows, this external field. Mu is in green here, it links with the body. And so what it's saying is that if you've got a larger field and the permeability of the body is large, it allows magnetic field to go through it, then you're going to get a big B, which is the flux going through the body here. So I much prefer it in this form. It makes more sense to me. So this is about the flux of the magnetic field going through the body and the magnetic flux. So this, I think, I also don't always appreciate because I don't know how that fits in with magnetic modeling. Whereas this seems to make more sense to me. But yeah, these are the two equations, this one up here and this one down here. And sorry, I've left off a little pink line here that I think have befuddled me for many years.